Yeah, first, thanks everyone for, either coming out and waking up this morning or potentially staying out and rolling in this morning. So, and like Larry said, we're here to talk about some radio stuff, so let's have fun. So first, a little bit about me. Like Larry said, my name's Blake. I'm a consultant on the industrial control system team at Mandiant, a FireEye company, as the slides will remind you throughout the day. I've been a radio hobbyist for about the last 15 years and have been using radio more and more in my professional life for about the last 3 to 5. I started my career in critical infrastructure security about 5 years ago, working in electric power generation for a company in the US Midwest, Alliant Energy, and more recently spent some time as the security engineer liaison for the information security team at Amazon to our fulfillment, transportation, and logistics practice, where I got to play with all of our fun robots. So today we're going to talk about trends in industrial wireless communication and the exploitation that is possible with the additional attack surface that wireless provides, and how most importantly, how you can get started understanding the radio frequency environment in the systems that you protect. So first, a bit of background. Why radio at all? I think the natural answer to a lot of questions about radio in industrial environments is don't bother. What's the point? You're just opening up additional attack surface. But the reality is that lower per sensor component costs combined with the falling cost of storage decreases the marginal cost of tracking additional points of a process. That combined with cheap access to computational power and increasing availability of analytical tools means that engineers have more and more desire for more and more data, not just from the process itself, but also sometimes less critical points that weren't worth tracking before. Things like machine performance data for predictive analytics and the IIoT, so shots, right? But why radio? So engineers are limited by the practical constraints of running additional I/O. Most DCS I/O cabinets look a little better than that, but there still is just the fact that running an additional cable to every sensor just doesn't scale. Sensor placement is limited when you have to run cables to every drop, and with the availability of ultra low power embedded systems and sensors, you have the ability to monitor additional points in your process with no additional power or communications cabling, sometimes for months or years on end. There's also the field. So wireless communication has always been the backbone of long-distance SCADA communications and telecommunications networks, transporting signals reliably over long distance to very rural areas that are poorly served by traditional ISPs and telecoms has always been the provenance of microwave communications. And fundamentally, some systems just move, like my old friend, the Kiva robot there. Systems like robots, trains, planes, automobiles aren't stationary and need to be reached with critical control traffic wherever they happen to wander. But yeah, fundamentally, this isn't the pitch for the Wonderware Expo over in Henderson. So why do we as hackers care about industrial RF? The threat model is fundamentally different than hardwired networks or hardwired I/O because of physics. It's fundamentally public. No antenna is perfectly unidirectional in practice, and many systems are point to multipoint or multipoint to multipoint meshes, which necessitate the use of omnidirectional radiating antennas, at least in some endpoints. Even those systems that are designed to be constrained within a single facility often leak through the walls, and the receivers on those systems may be sensitive enough to pick up signals that are sent from outside. So the types of attacks that end up possible, I really encourage everyone that's here and interested to check out the talk from yesterday. Radio Exploitation 101. That was Matt Knight and Mark Newland from Bastille. Their slides are already up on the DEF CON Media Share, so I'd really, really suggest checking that out. They go into detail about the form of several wireless attacks. Most common, obviously, denial of service or jamming. But this is a very well-known and well-understood reliability issue for wireless systems engineers, with decades and decades of research, mostly going back to military electronics warfare. So this threat is generally very well understood and accounted for by any system engineer who's considering the use of wireless communications in practice. But protection from other types of attacks, the type that we typically see on IP or IT style networks, have traditionally relied over time on protection by obscurity, which is everyone's best friend. So things like data injection, malicious device association with networks have typically been dismissed over time as simply not needing treatment due to the lack of skills and lack of availability of open source equipment to attack wireless implementations. So what changed? So now we're here, that's the background, and you're all here because you want to be radio hackers too. Maybe you've even walked through a plant with a USB wireless card running Kismet before. Maybe you've even found some rogue access points that are stuck in an employee's drawer with a power cable drilled through the back of the desk to feed the AP, just things like that. So 802.11 has its benefits in that there's off-the-shelf hardware, purpose-built for security assessments even, available online. The same applies to Bluetooth and to some extent even RFID. But historically, the challenge has been that for every protocol and frequency pair that you want to assess, you require either the purchase or the design and fabrication of purpose-built hardware, which is a challenge, again, for scaling arbitrary security assessments across multiple types of industrial facilities. So that's where we enter SDR. So that's the real heart of the talk today. Software-defined radio is a family of applied digital signal processing techniques that leverage high-speed analog to digital converters, that's the far right hand of that board, as well as DSP algorithms implemented in FPGA hardware interfaced to a companion CPU as a peripheral. So those are a lot of words, but practically what it means is that it frees us from the need to implement specialized hardware for every type of radio system that we want to assess, understand, and characterize. So to the left there is a Edis Research USRP B210. That's a software-defined radio that covers from 70 megahertz to 6 gigahertz, so quite broad set of frequencies at an instantaneous bandwidth that's really only practically limited by the speed of the USB bus that you attach it to. And to the right, I just have a screenshot from GNU Radio Companion, which is the graphical user interface front end to GNU Radio. And this shows what's kind of become the canonical Hello World program of receiving wideband FM or commercial FM broadcast. So the goal today is hopefully with the brief overview we're about to give that you'd be able to get to this Hello World type program on your own with limited investment and maybe just an additional couple hours of your time. So to start, there's kind of three components, I would say, to succeeding with a software-defined radio project. One is the hardware, because there are some hardware requirements. The second is the software, which is really where your brain meets the problem. And the third is obviously the knowledge and theory that you have to understand in order to be at least skillful enough with digital signal processing to get something done. But the good news is that because of advancements in both open source software and open source hardware, this type of work is accessible, even to those of us, like myself, who don't have advanced degrees in electrical engineering. And the community that supports this type of work is very strong and helpful, as I've found over time. So to start with the hardware. So even until relatively recently, software-defined radios had a serious price constraint. We're talking, professional test equipment running in the tens of thousands of dollars to even get started. But the good news is, over the last 5 years, primarily due to the reduced RF integrated circuit component cost, driven by development of 4G networks primarily, the cost has been falling and continues to fall to get started. So the most common way people get started is with an RTL SDR dongle. This is a general term for a family of USB devices based on a Realtek integrated circuit chipset. They are receivers only, so they're relatively limited, with a general range of about 40 megahertz to 2 gigahertz, which is great for starting. It gives you enough to do that Hello World program that we saw on the last slide. It also provides sufficient coverage of some industrial frequencies. For example, the unlicensed industrial, scientific, and medical bands at 430 megahertz and 900 megahertz in the US. But because they top out somewhere between 1.7 and 2 gigahertz, you lose out on the unlicensed 2.45 gigahertz ISM and 5 gigahertz and above licensed and unlicensed space. So enough to get started, enough to learn, enough to get dangerous, but once you get the taste, you'll probably want to move up to some of these fantastic, really hobbyist-grade gear. So for about a single order of magnitude increase in price, we're talking about between $300 and $400, you can move up to a really full-featured and sensitive transceivers. So something that's capable of both receiving signals, decoding them, and actually transmitting signals that you synthesize in software. I cover a few here. They range between, in their RF front ends, between several hundred kilohertz up to about 4 gigahertz. I believe the hack RF will get up to 6 gigahertz, but suffers some performance degradation above 4. They have relatively wide bandwidth, relatively sensitive receivers. So really, if you want to toy around, reverse engineering your garage door opener at home, or even doing some simple assessments in your own environments or a client's environments, it is enough to get started. The industry standard, really, though, for professional grade gear are the USRP line from Edis Research. I have no affiliation to them, don't consider this an endorsement, but it is what I use for client engagements. Very well regarded in industry. The prices range into the thousands here, but low thousands. And so if you have a commercial need to actually support repeatable assessments, it quickly starts to make sense. These cover, like I mentioned, I think a slide or two before, up to 6 gigahertz out of the box. At an incredibly wide instantaneous bandwidth, giving you a lot of flexibility for design and synthesis of your protocol decoders. So, good times. That's the hardware. Onto the software. Really, the heart of all of this is GNU Radio. GNU Radio is essentially a set of C libraries for digital signal processing algorithms. But the good news is that it also ships with a very nice GUI front end called GNU Radio Companion. And what GNU Radio Companion allows you to do is essentially attack the problem as a visual programming language, building out a flow graph that describes the processing of your signal from source to sink, allowing you to manipulate the data along the way using both its standard library of DSP algorithms, as well as a large and growing set of community open source modules. I will have links to all of this. They're currently pushed to my GitHub, which I'll have a reference to at the end of the talk. So you'll be able to find all of these later. The next I put up there is actually what's pictured to the right. It's called GQRX. It's also an open source project, and its primary use is for exploration of spectra. So this is very helpful for identifying previously unknown signals or confirming your understanding of signals that you believe might exist but aren't sure exactly where they are or what they look like. This is where I start if I'm on a new engagement at a new facility. And it's also helpful for capturing those signals for later offline analysis. This is where having one of the slightly higher end SDRs really pays off. Because you're limited, the width here that you see on the screen is dictated by the instantaneous bandwidth of the RF front end of the SDR hardware. Simply what that means is that the wider the bandwidth, the less tuning around you're going to have to do to find new signals, the more you see at once. So this is where those, definitely moving into that hobbyist grade gear up from the RTL SDR has the biggest dividends is during this exploration phase. There are also options for automated scanning across wide sets of spectrum. One is called HackRF scan, which not surprisingly works with the HackRF and the HackRF only. But if anyone here in the talk has recommendations for me, I'd love to hear about other kind of automated scanning tools, especially any that implement the UHD hardware API. So come find me or raise your hand during the questions. We can talk. The last thing here is in Spectrum. I don't have a screenshot. This is a tool for offline analysis of a captured signal. So once you've maybe identified a new signal using GQRX, either one that you didn't expect or don't understand, you can use the recording feature of GQRX to capture a raw IQ sample and open it up in Spectrum. This gives you a similar view to what you're seeing in GQRX, but critically what it allows you to do is pick out a single signal at a variable bandwidth from the capture and take derived measurements from it. So like a derived frequency domain plot. What this will allow you to do is start to reason about not just what the signal looks like in something like a waterfall graph, but actually the nature of the digital modulation of the signal. So when you're starting to try to understand the signal and build out a GNU Radio flow graph, you're going to have to make a critical set of decisions about where to start. And Spectrum gives you the tools to at least reason about and understand the protocol before you start trying to just implement a receiver blindly in the software. All right, so that's a lot. And I know if you're not taking vigorous notes, you probably don't know exactly where to go from here. And honestly, this topic is a little bit more than what you can cover in a half-hour talk, even to get started. But the good news is that even without a strong electrical engineering background, I really believe you can get started in Dangerous in about less than a day of reading and studying if you start with some of the resources that I have up on the slide here. So the first one, Michael Osman, who's the designer of the HackRF that was mentioned a few slides ago, has a video lecture series on his website openly available. So this is a training that he sells at actually relatively high cost, even earlier this week at Black Hat. But he makes at least a large portion of it, I'm not sure if it's the whole thing, available for free on his website, Great Scott Gadgets. Again, link will be in the GitHub. So at this point, I think he's up to either 8 or 9 video lectures. I've watched them all. It's a fantastic introduction to SDR in general, DSP fundamentals and terminology, and the HackRF in particular, since that's the device that he makes. But realistically, the lectures and the exercises in that series can be completed with any SDR, including really with an RTL SDR dongle. And even the first 3 or 4 lectures are really just on digital signal processing, and you can do just after downloading a copy of GNU Radio without any external hardware to get up to speed with some of the fundamentals. So that is definitely the place I recommend everyone to start. 8 lectures, about an hour long a piece, and you'll be up and running and quite dangerous in less than a day. The second resource I have here is a blog called Carriers Everywhere. Bastian Blessel is a European radio researcher with a security hobby, maybe, or security passion. And his blog is where he documents his experience reverse engineering multiple consumer and industrial protocols. his work has influenced my workflow quite a bit. And you'll see some of his open source software projects later on in the slides when we get into 802.15.4. And even his work with mobile traffic light reverse engineering informs the Modbus work we'll see in a couple minutes as well. The last two on here are textbooks. So if you have a little bit stronger interest and you want to round out your skills, practical skills with some theory, the first one there, Practical Signal Processing, is actually a very skinny textbook. And it's really made for people that are using DSP technology, not people implementing DSP technology. So it's the perfect level to familiarize yourself with the GNU Radio modules that are in the standard library to help make sense of terms like rational resampling, which fundamentally means multiplying by a constant and dividing by another one. Not nearly as complicated as it sounds, but without some of this guidance, it might seem a little maybe too intimidating at first. So definitely a good place to start, a couple hundred pages. The last one is a bit thicker. Complete Wireless Design. It's not DSP specific. It really focuses on the analog sides of radio frequency theory. So again, it's a good resource if it is something you'd like to take on a little bit more seriously. So this is a grounding in the fundamentals of oscillators, filters, mixers, radiators, all of the fun analog RF stuff. And when I use this book, it's to solve challenges that I run into that have to be addressed in the analog world. Some things simply can't be done in DSP. For example, due to limitations of the RF front end to your SDR. So an example of when I've used this book as a reference was on a recent engagement when I was asked to assess a signal for an oil and natural gas client that they were running at 11 gigahertz for their microwave backhaul. Well, the USRP that I have only goes up to 6 gigahertz, so how do I do this? There's really no SDR that covers 11 gigahertz, at least not at reasonable prices that I could find. So the answer really is in this book with the design of a RF down converter, which, again, seems intimidating. But once you break it down to its individual system components, it's something that I think anyone who's a hardware hobbyist can achieve with a couple weeks' effort. So these are all very good resources for someone getting started and for someone learning maybe over the course of their first 3 to 6 months of really digging into software-defined radio. Like I mentioned, links to all this on GitHub. All right, so enough background. When you get out into the field, what are you going to find? What do industrial signals look like? What are these protocols? Why not just 802.11? What are you going to find when you get out there? So the first example I brought today is a protocol called WirelessHART. WirelessHART is an international standard, process automation standard, developed initially by the HART Foundation and transferred to ISA as ISA Standard 100. It's a field communication layer for talking with sensors and actuators in the field. So there's layer 0 and 1 devices. It's just a wireless implementation of the HART protocol, which has a long history we won't get into. WirelessHART, though, depends on the 802.15.4 physical layer for transit. So that's the same physical layer that's used for Zigbee and other popular home automation devices. So we get lucky here, because there's been a lot of security research into home automation protocols that are built on 802.15.4 and Zigbee, and now we get to leverage that in our research into the security properties of WirelessHART for industrial automation. So a little background, it is a mesh protocol where individual sensors can store and forward messages to a network manager, which is typically a process manager or controller or gateway. So talking about the way that home automation security research paid dividends here, you might see in the top right-hand corner my flow block there for Wireshark. So to give you a little bit of a walkthrough here, this is the source block that defines the interface to the hardware radio that I have. where it defines the center frequency at the 2.41 gigahertz with some offset that I think I had defined up there. This block, the 802.15.4 OQ-PSK luckily, we don't really have to understand what it's doing in order to get what we want. This was implemented by Bastian Blessel, whose blog I mentioned earlier. But because this open source work has been done, we can just kind of ignore it. It's a black magic box. I plumb the lines in, I plumb the lines out, and in the top right-hand corner, I get Wireshark. And the good news about Wireshark is, good news about Wireshark is we know this, right? We're security researchers. We know Wireshark. This is exactly what I want to see. So once we get in to Wireshark, we can find some critical findings right off the bat just by looking into the 802.15.4 headers that Wireshark will understand out of the box. So if you look up here in the frame control data field, the highlighted field, as you might imagine, the fourth bit from the right there in the frame control, security enabled false. So what have I learned already about this WirelessHART implementation? Well, they're not leveraging the authentication and encryption features that are part of the 802.15.4 standard. But, critically, Wireshark doesn't ship with a WirelessHART protocol dissector out of the box. So I'm still left with this kind of mysterious payload in the bottom right-hand corner. And for all I know, maybe they're implementing authentication and encryption further up the stack. But what we find is, no. Turns out WirelessHART does use authentication encryption, as far as I can tell, in the messages that contain sensor values or control statements. But critically, what we've observed is that it does not give that treatment to advertisement messages. So the WirelessHART standard is closed. It's a bit pricey to access, and unfortunately, the license for the price that I paid does not allow me to release tools based on it. I'm lobbying internal for us to spend the cash so that we can open source the work that we've done. But we do need to work that out with the HART Foundation first. But what you'll see here is kind of the broken down version of the protocol message on the last slide. And what you learn from looking here is that, while malicious actors can't necessarily inject data values, what they can do is join the network as their own nodes by injecting advertisements, which potentially congest the link layer of the protocol and can affect network routing because it's a mesh. So yeah, if you see that Knight and Newland paper that I mentioned earlier, you might get some more ideas about how you can abuse open advertisements. And I encourage you to check out Joe Weiss's talk at this village this afternoon on why you care about vulnerabilities in process sensors and actuators, not just the controllers that they interface with. All right, last couple minutes. Modbus RTU. These radios are ubiquitous for process control in North America. Everyone knows Modbus TCP is unauthenticated, and so is its predecessor, Serial Modbus. So what happens when you take the bits from Serial Modbus, shove them into a modem, and push them out an antenna? Fun and profit. So pictured here, two really common modems. Both are, kind of by GE now. But this tradition extends all the way back to the 70s. It's not GE's problem necessarily. To now defunct manufacturers such as Daniels. They use a physical implementation, a modulation called AFSK, or audio frequency shift keying, which is essentially a 180-degree phase shift in an audio signal that's then encoded onto or modulated onto narrowband FM. So kind of similar to what you listen to in your car. In the case of the two radios pictured here, these are unlicensed 900 megahertz spectrum, but you can get them in licensed spectrum as well. The newer ones have encryption as an option, but it's generally, in my observations, not implemented because they'll ship in what's called a compatibility or interoperability mode with no encryption. So we'll see here, this gets a little more complicated, right? And the reason it gets a little more complicated is because this work hasn't been done in the open source literature before, so there is no black magic box for me to just pipe a signal through. But fundamentally, I think, again, with a few days of research, you could actually understand what's going on here. Mixing down to baseband, resampling to change the sample rate, You have an FM demodulation, clock recovery to match the beats, squelch, and then slice it out to binary and throw it out to a FIFO file sync. So what's that give me? Not perfect. It's cool enough, and we can simulate the matrix. So I don't even see the code. It's just, yeah, anyway. All right, so what I'd like to get to next from that is this. So a functioning integration with a software Modbus server or client. So this was actually done offline because of some issues with my implementation of the framing for Modbus, which we don't have time to get into the details of today because I'm out of time. But what you can see here is actually Pi Modbus essentially reading and writing coils as a Modbus client and decoding the Modbus server messages on the back end. So the implications here should be clear. These radios are deployed widely in North America for oil and gas pipelines, as well as municipal water systems, and they are fundamentally just public over the air. All right, so that's my time. I think I'm over by a minute. So I just want to thank Larry especially for dealing with me, the organizers, sponsors, and volunteers at the ICS Village, and all you guys for coming out and waking up this morning. That's about it. I do just want to mention I'm on the Mandiant team at FireEye Industrial Control Systems. We are hiring. So if this is the kind of work that interests you, you want to learn more, come talk to me after. And that's my GitHub that has the links from the talk, my Twitter if you want to continue the conversation that way. So that's it. Thanks so much. And if you guys have questions.